Hello everyone, it's March 30th. Let's do this subarray with k different integers. Given array nums and integer k, return the number of good subarrays of nums. A good subarray with the number of different integers in that array is exactly k. For example, has 3 different integers. A subarray is a contiguous. Okay, so we want to find the number of good subarrays. And a good subarray is one where the number of different integers is exactly k. So in the first case, we have 1, 2, 2, 1, 1, 2, 2, 3, 1, 2, 1, 2, 1, 2, and 1, 2, 1, 2. So so I want to find all the subarrays with exactly 2, right? Exactly 2 unique values. Counter, right? So we start. So most likely it's a 2-pointer as well. So with a sliding window. So we go here, and we have found 2, right? And oh yeah, keep going. So if we keep going, okay, so we'll hit this one. That's the first time we have 3, okay? So now we need to shrink it. That's not true. I think we should still have the same idea of finding the total number ending at each one. So ending at here is nothing. Ending at here we have 1 because that's when we have 1, right? We have 1. And ending at here. So what we want to do is to make sure that the current range the smallest possible, right? We find the smallest possible. How do you find the smallest possible? Just go through and then we find when one of them become 1, that is the smallest possible, right? Okay, that's the smallest possible. Then we can extend towards the left. But how far can we extend towards the left? Well, we can extend towards the left until another unique one is there, right? Yeah. So we go first index until we have the number is good, right? Until a number is good. Then we will shrink the left. How did we solve the one yesterday? It can't extend all the way to the left. That's how we solved it yesterday. So every time we extend, we count how many uniques there are. Okay. Becomes 0. So the right will go. We'll keep going until we find exactly k number of unique, right? And once we find exactly k number of unique, we'll move left until it hits a point where there's not k number of unique, right? So 1 becomes 0, right? So once that's found, then we know the total number of arrays ending at the right, right? We know that. It's just the left minus the pre, right? We'll do the same thing. So once we're done, then we move right forward. If we move right forward, does not increase the count, right? If it does not increase the count, then if it does not increase the count, then we will actually, because your left is pointing to a bad one because it moved forward, or maybe we don't move forward. No, we do move forward. Okay. Wait, hold on. What the pre should be? Because what I think pre should be -1. Right? If pre is -1, that means that's the previous, and then you go, you stop at the 1 that will make it, right? You stop there, and then you do the computation, right? And after you do it, you move it forward, and you decrement it. Now it becomes 0, right? And you remove it. Okay, and then left will go, or right will go, and if it's smaller than, then you don't do it. Right? If it's smaller than, you don't do it until it become take a k number of unique. Then you start moving on the I again, but you first reset the pre. The pre need to be here, right? Pre need to be in front, and then the left will go. Will decrement. Every time you go something with decrement, then we check. Right, as long as we still have, yeah, that's good. And then we still go. Yeah, and then we'll add it, and then right, keep moving forward. And each time right moving forward, if it's good, then we add the same number of count as before. Right, we add the same number of counts as before. Okay, I think this was pretty similar, right? Pretty similar. So but because it's a hard one, I don't have no intention. I mean, we can Java this. It's okay. It's okay. Let's Java this. Always forgot. Okay, so we need, of course, I is 0, j is 0, 3 is -1. Right. So in the build up, j first. No, j just keep moving forward. Every time we just, and I also need a counter. 2 times 10 to the 4. Yeah, we need a counter. Okay. Maybe the j just forward, right? Because j equals to 0, j is smaller than nums dot length. J plus plus. So I don't do this. We increment, say counter dot put nums j. Okay. Then counter dot get or default nums j. Default will be 0 plus 1, right? If counter dot size equal to k, all right, then we need a res as well. If it's equal to k, now I think I'll do the while first. So while counter dot size is larger than k, right? If it's larger than k, that way I need to move I. I need to move I. So you're saying I will stop at a point where we can say if counter, of course, I and I need to smaller than j, right? So if counter nums get nums I, if this is larger than 1, okay, then we say counter dot get dot put nums I counter get nums I -1 and I plus plus, right? If it's larger than 1, then we can remove it. Then move to the next one, and then we check if not, right? If it's equal to 1, right? So it's else. Now it's equal to 1. That's when we are going to stop, right? That's where we are going to stop. It's equal to 1, and I don't want to. Actually, I don't like it. I think we should first do this one. So we get it, and then we say if this is equal to 0, Wait, hold a second. Hold a second. No. We have more than k, so we have to keep going. So every time we remove one, and then we remove one, and then I++, then we check if it's good, right? We check if it's good. And yeah, this is, so we'll put it -1, right? And then I++, okay? Then we'll check. Well, actually, we need to do the check. If counter.get nums I becomes 0, then we should say counter.remove nums I, right? We didn't take it out. And I++. Then come back up, we'll check. Now, counter.size is equal to k, right? Counter.size is equal to k, then we drop out. So when we drop out, counter.size will always equal to k, right? It will always equal to k. So what do we do when the counter size is equal to k? So for the current, I am just going to say res sharp plus equal to I minus pre, right? I minus pre, because I is pointing to the first one. That makes it good, right? And what about pre? How do you update the pre value? Because J keeps moving forward. Actually, this is not right. This is not right. Because J shall stop the first time that's equal to K, right? J shall stop. We shall say if size is equal to K, right? That the first time the size is equal to K. Then I need to move forward. No, it is when it's larger than K, right? When it's larger than K, then yeah, if it's larger than K, then we put pre up. And then we start to remove things. Okay, so I think this is counter.get nums dot size. If it's equal to K, right? Once it's equal to K, wait, hold on. No, not equal to K. Once the first time it's larger than K, right? Then pre shall equal to I. First time is larger than it's guaranteed we're gonna move, so we move pre up, and then we will move I, right? We'll move I until, so this one I remove it. If it's equal to 0, then I remove it, I++, right? And then, so I will pointing at the right position, right? I will point in the right position. K, the pre will be pointing at whatever the previous position that is good, right? And then now this is bad, so we start going this, still bad, right? Still bad. Boom, now we are good. So anything that No, that should not be where the pre stays. So if it's larger than k, I shall go forward, right? At the previous position, we get something, and when boom, we get too much, then I need to move forward, right? It's still larger than k, so this cannot, these cannot go, cannot go, cannot go, cannot go, cannot go. Should be the first time, right, that I is not. That's where the p shall stay. That's where the pre shall stay. The pre shall stay here, right? And then I shall keep going forward. I shall keep going forward until it hits a point where I shall keep going forward until it hits a point where from I to j is the minimum possible. Okay, so this is not right. And then if it's larger than k, we'll go until we get out. When we get out, counter.size shall equal to k. And I shall point into a position, the first position, then make it equal to k. So we shall reset pre. I think pre is I minus 1. Right, pre is I minus 1. Yeah, it's this position. Right, so remove it, then that will become this. And then we say pre equal to I. Right, pre equal to I. Now get out. Okay, get out. Now what we're gonna do is while counter.size equal to k and I is smaller than j. I mean, we actually don't even need to check this. Oh, we actually do. We do need to check. And this has to be this. Then we say if counter.get nums I is equal to 1. Because I want to stop at a position that I want to stop. This is the position, because if I take this away, it's going to be smaller than k, right? So if this is equal to 1, then we shall break. All right. If it's not equal to 1, then we can do counter.put nums I counter.get nums I minus 1. Right, and then I plus plus. Keep moving forward. Size is good. Then we go, 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 go. Yeah, we can probably just do it this way. Well, it's larger than 0, right? Well, it's larger than 0. Then I move it forward until we have it's equal to 0, then we get out. So now I is in a good position. Right, I is in good position, then we can say I minus pre. Okay, now next time we go up. Right, next time we go up. Then what if my nums j is the same value? So counter size is still k. But then it's larger than 1, so I can move forward. So every time when we do is always make sure that we have in this window the correct number of unique. Right, the correct number of unique. Right, the correct number of unique. And we always have the pre as pointing to something, because like when we have more than k, right, then we always try to move forward, and then we see, like if it's 0, then we will remove it. Then that is the position, right? That is the position the pre should be, because that's where we will have more than k, right? That point is where we have more than k. So record that. So yeah, if I add a new one that gets more than k, then we shrink I. I will shrink I until we shrink to a point where it is k again, right? We shrink to a point where it is k again, and that's where we need to put a pre, right? That's where we need to put a pre. And now we're in the territory of the good one, right? Of the good one. So I need to keep moving I forward until I reach a point where that's the minimum length, right? When that's done, and everything towards the left will be part of the deal, right? It'll be part of the deal. Okay, let's see if this one works. Nope, does not work. Okay, so let's see the first example. So counter 1 is 1. Not larger than 1, so nothing does. And then I minus pre. Oh, I already minus pre. I probably need here to say if counter dot size is equal to k. Right, if it's equal to k, then we do this. Otherwise, we don't do it. Okay. It is likely that there might be some edge case I haven't considered. Totally possible. Okay, let's take a look. Oh, that looks good. I'll try this. Not bad. Not bad at all. Okay. What type of solution is this? Sliding window. Sliding window in one pass. It's been like what, a whole week, right? Is this considered one pass? I mean, you can do sliding window in less than this, right? Yeah, weird. That's weird. I'm not sure if I'm exactly doing this, but it's definitely something similar, right? It's definitely something similar, because this, my solution is indeed it's one pass, right? It is one pass, whatever the one pass means. And I started to like this kind of thinking, right? You get the minimum possible, and each time you extend, you add. Once you get too much, you need to shrink. But when you shrink, you need to get the previous position, and then get a new position. So you have the total count. Yeah. Okay. Not too bad. And no gonna to do this, so let's just end it today. And I'll see you guys tomorrow. Adios.